Before anything was observed, nothing needed to be explained. The universe did not begin with a question. It did not wait for a witness. It did not pause for a mind to arrive. Reality existed long before anyone wondered whether it existed at all. And yet, almost without noticing it, we grow up believing something very different. We grow up believing that reality begins where observation begins. A child closes their eyes, and the world seems to disappear. They open them again, and everything returns. Very early in life, we learn to associate seeing with existence. Richard Feynman would say this is where confusion quietly begins. Not because the idea is foolish, but because it is too natural. Physics, as Feynman insisted, does not start with equations. It starts with how we think, with the words we choose, with the questions we assume are meaningful. We casually say things like, when we look at a particle, when an observer watches, if nobody observes it. And hidden inside these sentences is an assumption we almost never examine, that observing is something special, that it is passive, that it is separate from the world. Feynman spent much of his life trying to untangle this mistake, because in physics, nothing ever merely looks. There is no silent watching, no detached awareness, no moment where nature pauses to see if someone is paying attention. There is only interaction. Before we talk about electrons, before we talk about experiments, before we talk about quantum mechanics, Feynman would stop and ask a quieter question. What do you actually mean by observing? In everyday life, observation feels harmless. You look at a tree. The tree does not change, at least not in any way you notice. You look at the moon. It stays where it is. You turn away. It remains. And so we build an intuition. The world exists independently, and observation simply reveals it. That intuition works beautifully for chairs, planets, and sunsets. Physics becomes strange only when we try to extend it to the deepest layers of nature. Feynman never said the quantum world is mysterious because it is mystical. He said it is mysterious because our everyday intuition breaks. We are used to thinking in terms of objects, solid things, little pieces of reality that simply sit there, waiting to be noticed. But the deeper physics went, the more this picture dissolved. Not suddenly, not dramatically, but patiently. What emerged was not a universe of things, but a universe of events, interactions, processes, relationships. And this is where the word observer starts causing trouble, because when we hear it, we imagine a person, a mind, a conscious experience. Feynman meant none of that. An observer in physics is not a human being. It is not awareness. It is not intention. It is not thought. An observer is simply something that interacts, a detector, a screen, a photographic plate, a cloud chamber, even another particle. There is no privileged role for consciousness. Nature does not behave differently because a mind is present. Feynman was very clear about this. What changes outcomes is not being watched, but being disturbed, and disturbance is unavoidable. You cannot measure something without touching it. You cannot observe something without becoming part of the interaction. This is not a philosophical statement, it is a physical one. And yet, people kept asking the same tempting question. But what happens when nobody looks? Feynman disliked this question, not because it was forbidden, but because it was misleading. It assumes that looking is something special. It assumes that the universe needs a witness to be real. Physics makes no such claim. The universe does not collapse into being when observed. It does not fade away in solitude. What changes is not reality itself, but what can be said about it. This distinction mattered deeply to Feynman.
Physics, he insisted, is not a story about what things are. It is a framework for predicting what will happen when systems interact. Nothing more, nothing less. When we perform an experiment, we are not uncovering a hidden script that was always there. We are creating a situation in which outcomes can occur. And quantum mechanics, in Feynman's view, does not describe reality directly. It describes probabilities, not because nature is confused, but because that's the most accurate language we have found. At the smallest scales, nature does not give us certainties, it gives us likelihoods, and those likelihoods depend on the entire experimental setup. Change the setup, and you change what can be predicted. This is why the idea of a detached observer falls apart. There is no neutral standpoint outside the experiment, no place to stand from which one can simply watch without influence. The observer is part of the system because measurement is an interaction. This is not optional, it is fundamental. And yet, something about this still unsettles us. We want to know what is really happening when nobody is watching. Feynman's response was calm. He would say, "That question assumes there is a single answer." But physics does not promise a single hidden reality waiting to be revealed. It promises a set of rules that accurately predict outcomes. And remarkably, those rules work. They work better than anything humanity has ever devised, even if they refuse to satisfy our intuition. Feynman believed that our discomfort comes from expecting too much. We want physics to tell us how the world feels, but physics only tells us how the world behaves. The mistake is not in the theory, it is in the expectation. And so, before the observer, before the question, before the measurement, there is simply nature. Not waiting, not hiding, not undecided. Just doing what it does.
One of the most persistent confusions in physics comes from a single, ordinary word: looking. We say we look at a particle. We look at an atom. We look at the outcome of an experiment. And without realizing it, we import into physics everything that looking means in daily life. Looking feels passive, harmless, as if the world simply reveals itself while remaining unchanged. But physics does not work that way. Feynman was relentless about this point. He repeated it in lectures, in books, in conversations. You cannot observe something without interacting with it, and interaction is never neutral. In classical physics, this was easy to ignore. You can look at a planet without noticeably altering its motion. You can measure the length of a table without changing the table in any meaningful way. The disturbance is there, but it is so small that it does not matter. Quantum physics did not introduce a new kind of disturbance. It simply revealed that disturbance was always there. At very small scales, you can no longer pretend that measurement is gentle. To measure position, you must interact. To measure momentum, you must interact. To measure anything at all, you must exchange energy, momentum, information. There is no free glance. This is not because particles are delicate. It is because measurement is a physical process. Feynman emphasized this repeatedly. An experiment is not a question asked politely. It is a situation created deliberately. You build an apparatus. You choose what it can detect. You decide what counts as an outcome. And nature responds according to that setup. Not because it cares, but because interaction has consequences. This is why Feynman rejected romantic interpretations of the observer. The observer does not collapse reality by being aware of it. Reality changes because something happened. A photon struck a screen. An electron triggered a detector. A system interacted with another system. That's all. When people say the act of observation changes reality, Feynman would quietly correct them.
Observation does not change reality. Interaction does. And interaction is unavoidable. Consider the famous double-slit experiment. If you try to determine which slit a particle passes through, you must place a detector. That detector interacts with the particle. The result changes. Remove the detector, and the result changes again. Nothing mystical occurs. The experiment is different, so the outcomes are different. This is not surprising. What surprised physicists was how deeply this principle applied. There is no hidden version of the experiment that runs independently of how you choose to observe it. The setup defines what questions are meaningful, and quantum mechanics answers only those questions. This is where probability enters, not as a sign of ignorance, but as a fundamental feature of how nature behaves under interaction. Feynman insisted on this distinction. Probability in quantum mechanics is not a placeholder for unknown details. It is the most precise description possible. When we say the particle has a certain probability of being detected here, we are not saying it secretly has a definite position. We are saying that this is what nature allows us to predict, nothing more. This made many people uncomfortable. They wanted to know what the particle really did between measurements. Feynman considered this question a distraction, not forbidden, just unproductive. Because physics does not deal in unseen narratives, it deals with predictions. If two different stories produce the same predictions, physics has no reason to prefer one over the other. And if no experiment can distinguish between them, then insisting on one is a matter of taste, not science. This is why Feynman resisted attempts to explain quantum mechanics in classical terms. Any explanation that feels intuitive is usually wrong, not because intuition is useless, but because it evolved for a world of tables and trees, not for electrons and photons. He often warned students against the desire to visualize too much. Visual models are helpful, but they can also mislead. Quantum mechanics works even when we stop trying to picture it, especially then. Measurement, in this view, is not about revealing pre-existing facts. It is about defining what facts can exist. This does not mean that reality is vague or arbitrary. It means that facts are contextual. They depend on how systems interact. Change the interaction, and you change the set of possible outcomes. This is not philosophical relativism. It is experimental fact. Every experiment confirms it. And yet, we still struggle with the idea. We want the world to have definite properties at all times. Feynman understood this desire. He shared it. But he did not let it override what experiments actually showed. Nature does not owe us comfort. It only owes us consistency. And quantum mechanics, as strange as it may feel, is consistent. It produces numbers that match reality with astonishing accuracy. So instead of asking what the particle really is when unobserved, Feynman suggested a different approach. Ask what happens when systems interact. Ask what can be predicted. Ask what experiments confirm. Everything else is storytelling. This does not mean that deeper understanding is impossible. It means that understanding takes a different form, not a picture, but a framework, not certainty, but probability, not observation as watching, but observation as participation. The observer is not special. The observer is simply part of the experiment, and the experiment is part of nature. Nothing stands outside.
At some point, every discussion about observation runs into a quiet resistance, a feeling that something is being taken away. People listen carefully, they follow the logic, and then they ask, but surely something must still be happening when no measurement is made. Feynman never denied this. Of course, things happen. Particles move, fields fluctuate, interactions unfold. The mistake is not in believing that nature continues on its own. The mistake is believing that physics must describe what happens in the absence of interaction with the same precision as it describes what happens during interaction. This distinction mattered deeply to Feynman. Physics is not a catalog of everything that exists. It is a method for organizing experience. It tells us how to calculate what we will observe when we perform an experiment. It does not tell us what the universe is doing when we are not asking questions that can be answered experimentally. This is not a weakness, it is a strength, because it keeps physics honest. When physicists tried to go further, to imagine precise hidden behaviors between measurements, they often ran into contradictions. Different imagined stories led to the same measurable results. Nature gave no hint as to which story, if any, was true. Feynman's position was simple. If two descriptions predict the same outcomes, physics does not choose between them. Reality does not care which mental picture we prefer. This is deeply unsettling for the human mind. We want the world to have definite answers, even when no one is checking. We want continuity, not just of behavior, but of description. Quantum mechanics refuses this demand, not out of defiance, out of consistency. Consider again the idea of disturbance. In classical thinking, disturbance is an accident, something unwanted, a flaw in the measurement. In quantum mechanics, disturbance is fundamental, not because nature is fragile, but because interaction cannot be undone. When a particle interacts with a measuring device, they become correlated. Information is exchanged, energy flows, momentum shifts. There is no way to separate what is measured from how it is measured. This is not a technical limitation that better instruments could solve. It is built into the structure of physical law. Feynman emphasized that we must accept this without embarrassment. The world is not required to match our preferences. It only needs to be internally consistent, and quantum mechanics is. It does not say that particles lack properties. It says that certain properties cannot be simultaneously defined within arbitrary precision within a single experimental setup. This is not about ignorance. It is about structure. The structure of interaction determines the structure of description. And description, in physics, is everything. Feynman was careful with language. He warned against saying that a particle has a position or has a momentum independently of measurement. These words come from classical habits. They suggest permanence where there is only context. A better way to think, the way Feynman encouraged, is to say the particle behaves as if it has a certain position when measured in this way, and behaves as if it has a certain momentum when measured in another. The phrase "as if" is crucial. It reminds us that we are dealing with descriptions, not metaphysical declarations. Physics does not claim to reveal the inner essence of things. It claims to provide rules that connect preparations to outcomes. This modesty is often misunderstood. People hear it and think physics is incomplete. Feynman thought the opposite. He believed that insisting on answers physics cannot give is what creates confusion. When we ask questions that experiments cannot answer, we should not be surprised when nature remains silent. This is especially true for questions about what happens between measurements. Between interactions, quantum mechanics does not provide a single classical narrative. Instead, it provides a mathematical framework that allows us to calculate probabilities for future interactions. That framework works. It works so well that no competing theory has ever surpassed it. And yet the discomfort remains. We want to imagine a particle following a path. We want continuity. Feynman acknowledged this desire, but he also warned that visualizing such paths often leads to error. In quantum mechanics, particles do not follow classical trajectories. They follow rules, rules that govern probabilities, rules that connect actions to consequences. Nothing more is promised. Nothing less is delivered.
The observer in this picture does not create reality. The observer participates in a process that defines what can be said. Reality is not vague. Our descriptions are limited. And those limits are not imposed by ignorance, but by the nature of interaction itself. This is a subtle point, and Feynman knew it. He did not expect people to feel comfortable with it. He expected them to feel puzzled. Puzzlement to him was not a failure. It was a sign that one was thinking honestly. He often said that it is better to admit confusion than to cling to a false sense of understanding. Quantum mechanics does not allow us to stand outside the world and describe it completely. We are always inside, always interacting, always part of the system, and physics, in its most careful form, acknowledges this without drama. It does not elevate the observer. It does not diminish reality. It simply tells us what can be predicted and what cannot, and that, for Feynman, was enough.
At this point in the discussion, many people begin to feel uneasy about a particular word, probability. To everyday thinking, probability sounds like uncertainty, a lack of knowledge, a temporary stand-in for ignorance. If we knew more, we assume, the probability would disappear and be replaced by certainty. Richard Feynman was very clear. This intuition is wrong. In quantum mechanics, probability is not a symptom of incomplete information. It is the most complete description available. This idea is difficult to accept because it contradicts how probability works in ordinary life. When we say there is a probability that a coin will land heads, we assume the coin will in fact land one way or the other. The probability reflects our lack of knowledge about initial conditions. But quantum probability is different. It is not a temporary measure waiting to be replaced. It is fundamental. Feynman emphasized this point whenever he taught quantum mechanics. The theory does not say, we don't yet know what's really happening. It says, this is what happens. The outcome of an experiment is not determined in advance in the classical sense. What is determined is the probability of each possible outcome, and that probability is calculated with extraordinary precision. Quantum mechanics does not fail to predict individual events by accident. It never attempts to. It predicts distributions, and those distributions match experiments with astonishing accuracy. This forces us to reconsider what we mean by reality. Feynman did not like grand metaphysical debates, but he understood that quantum mechanics quietly changes how we think about existence, not by declaring that nothing is real, but by showing that reality does not consist of definite classical facts at all times. Instead, reality consists of allowed possibilities and actual interactions. Between interactions, quantum mechanics does not assign a single outcome. It assigns a structure, a wave function. Feynman was careful here. He did not claim the wave function was a physical object in the usual sense, nor did he say it was merely a mathematical trick. He treated it as a tool for calculation that worked, and for him, that was enough. When people asked whether the wave function was really real, Feynman often resisted the question, not because it was meaningless, but because it led away from what physics does best. Physics does not tell us what things are in isolation. It tells us what happens when systems interact. The wave function encodes all the information needed to predict outcomes. It is not a picture of reality. It is a rule book, and the rules are probabilistic. This makes many people uncomfortable. They want to know which possibility is the real one before measurement. Feynman's response was calm. There is no fact of the matter that physics can access. The question assumes a classical answer where none is required. Quantum mechanics does not say that a particle secretly chooses an outcome and hides it. It says that outcomes occur when interactions occur. Before that, there are probabilities. This does not mean that reality is fuzzy or vague.
It means that reality is not composed of classical properties waiting to be revealed. Reality at the quantum level is structured differently. It is structured around interactions, around transitions, around events. Feynman often explained this using the language of processes rather than objects. Particles are not little balls moving through space along well-defined paths. They are elements in a mathematical framework that predicts interactions. They are what they do. This shift in thinking is subtle but profound. It removes the need for a privileged observer. Nothing collapses because it is seen. Outcomes occur because interactions occur. And probability is not a failure of description. It is the description. Feynman was fond of saying that nature is not classical, and it is pointless to try to make it so. The success of quantum mechanics comes from accepting this without apology. When we stop demanding that nature conform to our intuition, the theory becomes clear. Strange, but clear. The probabilities are not subjective, they are objective features of the theory. Two physicists with the same setup will calculate the same probabilities. Experiments will confirm them. There is nothing arbitrary about this. What is missing is not information. What is missing is a classical picture. And that picture, Feynman argued, is not something we should expect to recover. Trying to imagine what really happens between measurements is like trying to imagine what sound looks like. The question itself imports assumptions that do not apply. Quantum mechanics does not deny reality. It denies that reality must resemble our everyday experience. And this is why the role of probability is so central. It is not a placeholder. It is a statement about the structure of nature. The observer does not choose outcomes. The observer creates conditions under which outcomes can occur. Nature responds with probabilities, and when interaction happens, one outcome is realized, not because it was selected by awareness, but because interaction occurred. This is not mystical, it is mechanical, it is mathematical, and it works. Feynman found beauty in this, not comfort, but honesty. The universe does not pretend to be simpler than it is, and physics, at its best, does not pretend to know more than experiments allow.
There is one question that appears again and again whenever people encounter quantum mechanics. It sounds innocent, even profound. Does it exist when nobody looks? Richard Feynman did not forbid this question. He did not mock it, but he did not treat it as deep either. To him, it was misleading, not because it was meaningless, but because it smuggled in assumptions that physics does not use. The question assumes that existence is something that switches on and off depending on observation. It assumes that looking is an action separate from interaction. And it assumes that physics is supposed to answer questions framed in everyday language without first examining the language itself. Feynman was always wary of such assumptions. He believed that many confusions in physics arise not from the equations, but from the words. When we ask whether something exists when nobody looks, we are importing a classical idea of existence, an idea shaped by tables, chairs, and planets. In that world, objects have properties whether or not anyone checks. Quantum mechanics does not deny that the world continues. What it denies is that properties exist in the same way independently of interaction. Feynman's response to this question was practical. He would ask, what experiment could possibly answer it? If no experiment can distinguish between two possibilities, physics has nothing to say about which is true. This is not avoidance, it is discipline. Physics advances by asking questions that experiments can answer. The question, does it exist when nobody looks, cannot be translated into an experimental test without redefining what look means. And once you redefine it, you no longer mean what you thought you meant. If looking means human awareness, then physics has nothing to say. Human awareness is not part of physical law. If looking means interaction with any system, then the answer is trivial. Interactions are happening all the time. Particles interact with fields. Fields interact with other fields. Nature is never in complete isolation. So the question dissolves. Either it asks about consciousness, which physics does not address, or it asks about interaction, which is always present. In neither case does it reveal a hidden mystery. Feynman found this frustrating, not because people were foolish, but because they were asking the wrong kind of question. They wanted certainty where the theory offered precision instead. They wanted a story where the theory offered a rule. He often reminded his audience that physics does not explain why nature behaves as it does. It describes how, and it does so with remarkable success. Quantum mechanics does not say that the moon disappears when nobody looks at it. This popular caricature misses the point entirely. The moon is constantly interacting with its environment, with sunlight, with cosmic radiation, with gravitational fields. There is no situation in which it is not observed in the physical sense. And even if there were, quantum mechanics would still break down. It would still provide predictions for any future interaction. The problem arises when we try to imagine a detailed classical picture of what happens in the absence of measurement. Quantum mechanics does not supply such a picture, and it does not need to. Feynman emphasized that we should resist the temptation to fill in gaps with comforting stories. If two stories lead to the same predictions, then insisting on one adds nothing to our understanding. It only adds confusion. The question about existence when nobody looks feels deep because it challenges our sense of reality. But Feynman would say that reality has not changed, only our expectations have. We expected physics to provide a classical narrative at all times. It does not. Instead, it provides a consistent framework for connecting experiments to outcomes. That framework does not require that properties be defined when they cannot be measured. This is not a limitation to be overcome, it is a reflection of how nature behaves. The demand for definite properties at all times is a human preference, not a physical principle. Feynman was comfortable with this. He found it liberating. Nature does not have to explain itself in our terms. We have to learn to speak its language. And its language at the quantum level is probabilistic, contextual, and precise. Not vague, not mystical, just different. When we stop asking whether something exists when nobody looks and start asking what happens when systems interact, the confusion fades. The observer loses its imagined power. Reality regains its stability. And physics continues to do what it has always done best: predict. At the end of all questions, there is a quiet moment that physics never tries to fill. A moment where explanation stops not because it failed, but because it succeeded. Richard Feynman believed that the deepest mistake we make about science is expecting it to satisfy every kind of curiosity. Physics does not exist to comfort us. It exists to describe nature as accurately as possible. And sometimes, accuracy feels unsettling. Throughout this journey, we have followed a simple idea: that observation is not watching, that measurement is interaction, that probability is not ignorance, and that the observer holds no special power over reality. None of this diminishes the universe. It clarifies our place within it. We are not outside the world looking in. We are inside it, participating. Every experiment we perform is not a passive question, but an active event. We set conditions, nature responds. Not with answers written in advance, but with outcomes that follow precise rules. Those rules do not promise certainty, they promise consistency. And consistency is the true achievement. At some point, every listener asks the same silent question: is that really all there is? Feynman's answer, though rarely stated directly, was clear: yes, and it is enough. Physics does not tell us what reality feels like. It tells us how reality behaves. It does not reveal the ultimate essence of things. It reveals the structure of interactions.
When we accept this, a strange calm appears. We no longer need to imagine hidden stories playing out behind the scenes. We no longer need to ask what the universe is doing when nobody is watching. The universe is doing what it always does, interacting, evolving, following laws that do not depend on our presence. What changes is not reality itself, but what can be said about it. Knowledge in this view has a clear boundary, not a wall, but a horizon. Beyond it, there may be questions, but not all questions belong to physics. Feynman was deeply comfortable with this boundary. He did not see it as a failure of imagination. He saw it as intellectual honesty. To admit what we do not know is not weakness, it is precision. Quantum mechanics does not invite us to believe strange things. It invites us to stop believing things that are not supported by experiment. It asks us to give up the idea that reality must be classical to be real. It asks us to accept probability not as ignorance, but as structure. And it asks us to let go of the observer as a central character. There is no cosmic audience, no final witness, no privileged viewpoint. Only interactions, only outcomes, only rules that work. This does not make the universe smaller. It makes it quieter. And in that quiet, there is something profound. Not a mystery to be solved, but a mystery to be respected. Feynman once said that he could live with doubt, that uncertainty did not frighten him. What frightened him was false certainty. In this sense, quantum mechanics is not a story of confusion. It is a story of restraint, of knowing where to stop, of understanding that the goal of physics is not to replace wonder, but to coexist with it. The observer does not create reality. Reality does not wait to be seen. The universe simply continues, and we, for a brief moment, learn how to listen.